Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me as always is...
Robert Moore.
So, Robert, this is our 29th episode.
29. I am kind of flabbergasted that we're continuing to go that far.
You know, I'm going to go through all 29, and I'm going to get all the little snippets out of it and put like a blooper reel together.
Oh, Lordy. We might be able to sell that and make money.
Lots of material for the very first few podcasts, as you can imagine.
True.
Now, in this podcast, we do talk about all things science, in particular related to physics, astronomy, astrophysics, you name it, the weather.
Let's not talk about the weather. The weather's been entertaining, though.
Well, we are broadcasting live from the campus of the University of North Dakota in Grand Forks. I'm not going to say the rest of it because I say it all the time.
Okay. You want me to say that?
No. I was going to say we always say Grand Forks, North Dakota. Where else would the University of North Dakota be at? It wouldn't be in South Dakota, right?
Well, it could be in close stay.
Oh, there you go.
Oh, wait a minute. That's Fargo. I was still contend that somebody missed an opportunity with that, not putting a town in the northwest corner of the state called close stay. You know, with northeast, southeast quarter being Fargo.
Well, we can start a new gathering of people, a new community, and there you go.
Yeah.
You could be mayor, the first mayor of the town.
Who would want me as mayor?
Now, if you do have a question related to things that we haven't talked about yet, we do have a live chat that's running. Feel free to use it. So I see Mizuho's already added a contribution today. Thank you, Mizuho, for doing that.
Yep.
And also the fact that, you know, it's a good time to probably thank our Department of Physics and Astrophysics and the College of Arts and Sciences and the university.
They're letting us use this equipment.
Yeah, so. and it's their time, essentially, right? We're doing it during a normal workday for us at 3 o'clock local time.
Right.
And so we thank them all for allowing us to do this podcast. And the other thing, too, is what we say, of course, is our own personal opinions and not necessarily those of the institution or anyone affiliated with us.
Right.
So maybe that's why they do this, Robert. They allow us to do the podcast. Hopefully we'll slip up enough that they can just get rid of us. You see how that works?
I hope that's not the case, but yeah, I've been in that type of situation before and had to watch my P's and Q's, so I don't do it as much here as I probably should.
Now, one of the things that we do is we talk about the things that are in the news recently.
Right. And there's been some news come out. So.
And there has been. And it seems like every week there's something new going on. And in fact, in some sense, that's motivation.
Right.
To publish a new textbook every year on astronomy. And it's a good thing in terms of the news release. It's a bad thing in terms of if you're a student and you want to sell an old version of your textbook, they become unsellable once you go to a new edition.
Right.
Is my understanding anyways. But, you know, thankfully we do have things happening in astronomy every year that makes it worthwhile to at least update the information. It's not a stagnant field that never changes for decades and centuries. Things are always changing. And that's mostly driven, of course, by the introduction of new technology.
New technology, new instruments, just right on down the list. Yeah.
And so speaking about new instruments, so one of the things we talked about last day is the fact that Russia, you know, since the day when it was the Soviet Union, had tried to do a soft landing on the moon. And we talked about the fact that it actually crashed on the moon. So there was a bug somewhere. They're still investigating this, find out what happened to the spacecraft itself. But we know that it landed. It landed on the moon, but it was a hard landing.
It was a hard landing.
And those are a lot easier to do than obviously a soft, gentle landing.
You know, as the show that I like watching says, you know, just get us on the ground. That part will happen for sure.
Right. Exactly. And so we do have, since last week when we talked about this, we now have confirmation that the spacecraft has landed on the surface of the moon. This is the Luna 25 mission.
Okay.
So Robert, if you want to show our first slide of the day. This is actually photographic evidence then for this landing. And what you see in the central region is a bright area. In fact, if you click on that, I wonder if that will change. No, not clickable. Okay. So there is a contrast that you can get on the web if you look up the Luna 25 impact site. Just Google that. You'll see a little GIF file that somebody put together, NASA. And it's an image taken from the Lunar Reconnaissance Orbiter spacecraft, the LRO.
Yeah.
And it shows the same area of the moon before the crash landing and after the crash landing. This is the after the crash landing view. And the kind of the bright region you see almost in the very center of this image is the impact site of the Luna 25 spacecraft. We know that didn't exist before it landed, and it exists after it landed. So you can be pretty sure that this is the region where the lander actually crashed.
Now, I hadn't thought about this when I was looking at this image earlier, but it also shows some interesting physics that goes on in the impact, because that impact is a streak, whereas look at all the ones that are around it from asteroids and meteorite strikes, and they're all circular, but they all did not come in vertically. But what causes that difference?
Yeah, well, I mean, first of all, the brightness is one thing that catches your mind, regardless of the shape of it, is the fact that the soil in that area is extremely bright. So that's essentially a kick up of the soil underneath the layer of the sun. So that's been heavily weathered by cosmic ray impacts from the sun. And so, because the moon doesn't have an appreciable atmosphere at all. If you want to get really technical, there are like sodium atoms that hang on the surface that outgas from the moon and so on, and people call that an atmosphere. But to think about an atmosphere like we think about the everyday person, it essentially has no atmosphere. So you're walking in the vacuum of space if you're walking on the surface of the moon itself. And so you get that fresh soil that gets kicked up and exposed to the sunlight, and its reflectivity, its ability to reflect light, is not the same as the sort of weathered from space weather, not from wind and rain and so on, and your micrometeoroid impact of the soil and stuff.
Yep.
That fresh stuff that gets kicked up it reflects light a lot better, if you like, than the older soil that was on top. And that's one thing.
Right.
And the other one is just the trajectory where it's digging, where the line that it's coming in on, whether it's directly coming down or even coming out at sort of a grazing angle to the surface, that will give you the different sort of feature that you see in terms of the leftover after the landing itself.
And the other thing is the reason asteroid and meteorite hits are circular is the vast difference in kinetic energy. Even a small meteorite is coming in at thousands of meters per second, and it essentially explodes. So it's like a bomb went off. Whereas this probe, this lander striking, it didn't explode and kind of drug across the surface. So that's why meteor craters are usually round.
And you can actually do some experiment with this yourself if you're so inclined. You could put together, maybe an area, take a pan that you use to bake a cake in, whether it's round or it's square, it doesn't matter, and let's say fill up halfway with flour, right? And then even it off so it has roughly the same thickness across the pan. And then you can drop various objects from various heights and throw it in at different angles and get an idea of what type of impact, quote unquote, crater that those objects make.
And yeah, I put students through an experiment on that.
Yeah, and then
type of things.
And the thing about that experiment is once you're done, you can dig those objects out, add a little milk and sugar, and then actually have dessert out of them.
Meteor cake. Crunchy. Okay, I'm a bad person.
Now, the other thing that's been in the news, so this is the next slide if you want to show that, is once again, new observations from the James Webb Space Telescope.
Nice.
Now
this is pretty.
Yeah, it is. And what you're seeing here is the leftover debris, essentially, that is what we call a supernova remnant from a massive star that exploded, that was observed to explode, back in, and you guess it from the title, 1987. So this was in February 1987. Ian Sheldon, Canadian, yay, actually observed this supernova. He was down in Chile at the time working at Las Campanas Observatory and observed, the first person on the world to observe the appearance of essentially new star in the sky. So it was a previous existing star, Sandulik -69202. That's the name of the progenitor. It's a catalog name.
So it's a catalog name, so it had been observed.
Yeah, so -69, so that's south declination, -69 degrees south. 202 is the rest of the coordinate. And Sandulik was the person that put together this catalog of various objects in the south, or stars and so on. And essentially what happened is when this supernova went off and observed in 1987A, so in 1987 it was the first one of that year, so it was given the designation, the letter A afterwards. That's where that comes from. And so when the supernova sort of died down, then you can go back and look and see which star actually blew up and turned into the supernova.
Because it won't be there anymore.
Because it won't be. It was the one that no longer exists, So the star was there before it went off and it wasn't there after. So you know exactly which star it was. And that star, interesting enough, we talked a little bit about this on a previous podcast.
Okay.
But that star turned out to be a blue supergiant rather than a red supergiant.
Ooh.
Now, prior to 1987, when you talk about the evolution of stars and you talk about the fact that massive stars, these are stars that have a mass greater than about 8 times the mass of our sun. When they end their lives, they do so dramatically by blowing up in these supernova explosions.
Right.
And of course, in that explosion, the debris left over is hurled in all different directions, and you have what's left over called a supernova remnant. And the energy, if you like, of that explosion helps energize that debris. And sometimes what's left over is a very special object called a neutron star, and that can even energize gas and dust surrounding it.
Even further.
Even further. Most of it is particles that travel, that are traveling outwards, that run into other stuff, that boosts up the energy levels of the electrons. If you think about simple, atoms. And the electrons then, when they're at this higher energy level, they want to always come down to the lowest energy possible, and they do so by emitting light.
Right.
And that's part of this emission process where the light comes from and allowing us to see the supernova remnant. Now, this image, because it was taken by the James Webb Space Telescope, is an image in the infrared.
Okay.
Now, it's not like we haven't seen this object before in the infrared. For example, the Spitzer Space Telescope.
Did it look at it?
Yeah, took a picture of this.
1987, yes.
Yeah, so the Spitzer took a look at it. It was just the first time that we had a very large infrared telescope, roughly 6.5 meters in diameter.
As opposed to 0.8.
Right, looking at and that provides you then higher resolution. Plus its filter set, that is the wavelength that it does its observation at, is not the same as the Spitzer Space Telescope.
Right. Spitzer was tuned to just a few wavelengths, specific wavelengths, wasn't it?
Yeah, a lot less than what the James Webb, if I remember it. Plus, some of those wavelengths are really long infrared.
Right.
So, there you're looking at essentially light that's emitted by dust. So anytime you take dust and it's heated up a couple hundred degrees Kelvin, is the temperature scale we mostly use in science, then that emits profusely at infrared wavelengths, the dust.
Right.
Okay, so the dust itself had this, what we call thermal emission in physics.
Mm-hmm.
And just like, for example, you could look at the different stars and they have slightly different colors depending on the differences in their surface temperature. Right. And that's directly, thermal emission that's happening there. The hotter objects, that is the object, I should say, that has the higher surface temperature, most of their light comes out at shorter wavelengths than stars that have a lower surface temperature. I think we talked about that in the past as well.
Yeah.
But in case
and
you didn't listen,
we talked about the black body curve and all that, and this is all related to all
it's
that.
all related to that. Now, the interesting thing, once again, about the progenitor, that is the object that was responsible to create this supernova remnant to begin with, because it was a blue supergiant, it was actually smaller in size than a red supergiant of the identical mass. Okay, now the mass of it, it's hard to estimate exactly what was the mass of the star before it blew up. Estimates are in the order of roughly 20 times the mass of the sun. So let's just go with the number, 20 solar masses.
20 solar masses. That sounds reasonable.
But if you look at a blue supergiant star of 20 solar masses and compare it to a red supergiant star of 20 solar masses, the blue one is smaller in physical size. Okay. Which means that its surface temperature is going to be higher.
Is higher.
And that's the difference in color.
Things that expand, get bigger, cool off.
That's right, exactly. And the light shifts in the optical towards the red side, right, rather than going to the blue. So because this was a blue supergiant, that means it was smaller in size than if that identical star was a red supergiant. And because it was smaller in size, more energy of the explosion went into forcing that outer envelope of that star to blow off. And so it didn't become as bright as a normal supernova type 2, as we say. In fact, people catalog it a lot as the supernova type 2P, where P means peculiar. Because in some sense, it was the first blue supergiant, right? That went
to blow up.
Yeah, but don't forget, this is the nearest supernova to us since in about 400 years.
I was about to say, which galaxy was this one in?
Was in the Large Magellanic Cloud.
Okay.
So it is a nearby low mass or satellite galaxy to our Milky Way. And if you're interested in distances, you like to know the numbers and so on. And we talked about using like distance measurement as light years. So 1 light year distance would be the distance that light travels in 1 year.
Mm-hmm.
But you have to travel at the speed of light.
But you have to travel at the speed of light.
So this object is 168,000 light years away.
So relatively close by.
Relatively close by. Thinking in comparison, the edge of the observable universe, the light that we receive, left those galaxies over 13.5 billion years ago. They're over 13.5 billion light years away, right, without factoring in the expansion of the universe.
Right.
If you factor that in, well, they're actually, right now, if you could ask, where is that galaxy? How far would it be from us today, instantly, right now? It's on the order of about 45 billion light years away because of that expansion.
Right.
So given that this object is 168,000 light years away, it's in our backyard.
Mm-hmm.
So it's part of the...
When you go into the southern hemisphere, you can see the large and small Magellanic Clouds just fine with your naked eye.
Easily, and I've been there several times, and I've done that. I've looked up at the sky and have seen the large and small Magellanic Clouds. In fact, the name itself, Magellanic, means Magellan.
Magellan.
And Magellan reported his crew that remained when they got back to Europe after circumnavigating the globe in the 1500s. That's before the invention of the telescope. So the only way the crew on board that ship could see these objects with their unaided eye. So clearly they have to be observable to the unaided eye.
Probably easier to see back then due to less pollution, less light.
Well, if you're out in the middle of the ocean somewhere in the South Pacific, you're going to see these on a clear night.
Right.
And that means, people who lived in the southern hemisphere, they knew the existence of these objects in the sky for as long as they could look up and wonder.
Right.
It's just that people in Europe didn't know about it because they're below the horizon all the time.
Right.
And so since Magellan, of course, his origin is from Europe, then all that information and log books were then brought back to Europe. If I'm not mistaken, Magellan was killed during that voyage, so he physically never made it back to Europe.
I can't remember.
I believe
Magellan is just not one of the ones that I really... his name is everywhere, so clearly his mission succeeded,
But talk about a risky business going around the Earth in the 1500s.
Oh, yeah.
So talk about brave people. If you think about the explorers back in those times, they were extremely brave. You never know what kind of land you land on, whether or not there is anything between.
Whether the natives will be hostile or...
people living in different areas of land masses, you don't know what you're going to encounter. What about different animals that, as soon as you land, some native animal comes, sweeps it out of the sky and swallows you whole. You just never know, right?
That's it.
And there's all the stories and myths about sea creatures and all of those things. So you have to be extremely brave.
You did.
And you got to carry enough fresh water with you and food to make it. And hopefully you're not going to carry enough to make it back to Europe. So the idea is you go somewhere and land, and hopefully you're going to get food and water wherever you land. Well, what happens if there is no other land mass, or it takes you, like 10 years to sail around the Earth? You're not quite sure how large. I think you have some estimates, obviously, back in them days, right? But still.
Had an estimate since the time of Eratosthenes. So.
Well, yeah, and so you just never know if those are right or not until you actually do the experiment. You want to know? Do the experiment.
Well, that's what Columbus was really guilty of, is he had all these other people's estimates of how round the Earth was, and he came up with his own figures that were much smaller. So he thought it was a nothing jaunt to just go west and get to the Indies.
Wasn't that story where he was just before they sighted land, there was mutiny occurring on board the ship?
There was.
And so if it would have took a few weeks longer, then probably they might have turned around before they landed in North America.
Mm-hmm.
And the other misconception is people always say they discovered America. Columbus never landed
on America.
in the United States as we know it today.
Yep.
So
Well, anyway,
Anyways.
we should get back to the topic. So, I imagine you brought the supernova up for other reasons.
Yeah, so we want to go
Okay.
to the next slide. We actually have a detailed view of the supernova remnant itself. Now, when you first look at this, people think that everything you see here in light is part of the supernova event itself. It actually isn't. The only part that's part of the supernova is actually the sort of bluish color that you see near the center. And it's labeled here as the inner ejector or the keyhole. It looks sort of like a key
It
shape.
does, kind of, yeah.
Yeah, so people labeled that keyhole from that perspective. But that's actually the supernova remnant, that part. That's the material that has expanded out to a certain distance since 1987. Now remember, when we talk about the supernova exploding in 1987, that's when the light reached us that signified the explosion had occurred. That light has been traveling for 168,000 years before it reached the Earth. So you have to always bear that in mind when you're talking about astronomical distances or things that are very far away. Now, the other material that you see a little bit further out, so the different labels that you see here, for example, the equatorial ring and so on, this is material that was released prior to when that star went supernova. So it turns out that stars, especially massive stars, when they're near the end of their lives, they're very unstable. And they could have episodes where material then is ejected out into space. So if you like, a prior episode of mass loss occurred, and the particles that are traveling away from the site of the explosion eventually catch up for that material that was released many years before the event occurred, and they run into that material, energize it, once again causing electrons, if you like, to go up to the higher energy levels, and when they descend back down, they release that light, allowing us to see that today.
For those of you who want to see a star that hasn't gone supernova but is doing this in the process of blowing off pieces of itself, look up Hubble images of a star called Eta, ETA, Carina. I'm not going to try to spell Carina, but Eta Carina is a current high mass star that's in this process of just blowing out waves and waves of material.
And you want to know another one that's sort of in that spot, but not quite that much?
Betelgeuse?
Exactly.
Yeah.
And if you look at telescopic images that we've taken of Betelgeuse, you can see outflow of material, right? A stellar wind, as we call it, and burst, like a lot of stuff coming out. It looks irregular in shape, big lobes of material off to the side here and there. So that's at a very unstable part of its life also, whether it's ready to go and turn into a supernova the next
Tomorrow!
day or 100,000 years from now, we just don't know.
Right.
Okay. So this is interesting. In fact, if you look carefully, you'll see there's these dashed curves, one near the top called an outer ring, and there's one below, also an outer ring. In some sense, it almost looks like a champagne glass. You see a rim that would represent the top of the champagne glass tilted towards us, and then the stem, and then to the stand part of the champagne glass, the stand would represent the other ring, and that would be the furthest from us in projection. And and that was from an earlier mass loss, we think, when it was a red giant. So this is in the process.
It swelled up and then collapsed.
Yeah, and some of the material gets released, and that's what the particles are running into that material now and energizing it, sort of thing. And so there's a lot of sort of dynamics. A lot of things are changing on a relatively short time scale. People have taken images of the supernova remnant since 1987, essentially. Mm-hmm. And and you can compare it to image maybe that you took a year prior and a year before that, and a year before that, and you can see things changing on that sort of time scale as different.
Supernova remnants are some of the most dynamic things in astronomy, and Crab Nebula, this one. Let's see. Well, there's another.
The Vela supernova remnant is
the
one.
The Monosaurus one.
Yes, and Cassiopeia A is another one that we discovered. So there have been lots of them. It's just that there's never been one this close since the invention of the telescope.
Oh, wow. Right.
Right? Because the last supernova went off was in the early time of Kepler, and that's just before Galileo was using the telescope to observe the heavens. And so this is the nearest, closest supernova since the time that we've invented the telescope, and whether or not having telescopes in space, this kind of thing. And so this is where we're going to make our detailed study. Now, Robert, here's a very interesting question for you. Okay. What's at the center of this thing?
Of this one? You said it was about 20 solar masses? It's probably a black hole then. Could be a neutron star, but I'm betting black hole.
Okay, so to know what's at the center, of course, what do? You go make the observations.
Right.
Right?
Absolutely.
So ever since the supernova went off in 1987, people have made these observations, have looked for the presence of a neutron star, for example, and also for the presence possibly of a black hole.
It could have blown itself completely apart, though.
Now, what's one way that we can find neutron stars? Now, first of all, just to kind of let people know again, so we talked about also in the past on a different podcast what a neutron star is. So it's the end state of a massive star. Okay, there's like three end states that you could be. Number one, a white dwarf, and that's what our sun will turn into eventually. If you have more mass than our sun, let's say up to around 20 solar mass roughly, 20, 25, then the core that remains after a supernova explosion, our sun will not be a supernova, it turns into a planetary nebula. It's more of a gentle ending rather than this dramatic event that's for the high mass stars only. The core that remains is made up essentially of neutrons in this process of blowing up, and we call that a neutron star. So something collapses down to the size of a major city on Earth, let's say.
Right. A star the size of a major city.
Yeah, so it's extremely dense, and along with that, it has a very strong magnetic field as far as we know. Right. And that gives rise to this model that we call the lighthouse model to explain the fact that back in 1967, it was observed, this is the controversy with Jocelyn Bell, who was a graduate student in England, I think at Cambridge at the time. Her advisor, Anthony Hewish, were looking for objects that were basically flashing on and off at radio wavelengths. So they had built a special radio detector to look for these things. In most cases, people were looking at radio sources over long periods of time, like over several minutes. And anything that turned on and off rapidly, they chalked that up to earthly interference.
Noise.
So things like a spark plug in a car going by would generate this periodic noise that would change rapidly over a second or so.
Flicking your lighter on generates radio waves.
So no one was really looking for these changing emission, these pulses of radio observations, but they were picking them up, and Jocelyn recognized there was something here that may not be earthly interference. And so they did follow-up observations and so on. This led to the discovery, essentially, of what we call today pulsars. And of course, when they were discovered right away, you think of what is the cause of these? What is their inherent nature? And people suggest almost immediately, because it was already thought about, at least by some theorists, even before pulsars were discovered, that these were rotating neutron stars. And so if you got a neutron star that's rotating rapidly, what do I mean by rapidly? Well, some of these go around and make a complete rotation in 1/30th of a second, and some of them even shorter time scales. We call those millisecond pulsars. They go around once, in thousandths of a second of that order, that scale. So these rapidly rotating neutron stars, because they're strong and very dense, they're able to hang on to their material. It doesn't get flung away because of the rapid rotation.
Their breakup speed is much higher.
Exactly. And they have this strong magnetic field associated with them. And what happens is you get this beaming of radiation, which I mean electromagnetic radiation, light, that gets beamed in both along the north magnetic pole and in the south magnetic pole. And if the magnetic rotation axis is offset from the rotation axis of the neutron star, you almost can get in a situation you have like a lighthouse effect where this beam of radiation sweeps around in a cone-like fashion. And if the Earth just happens to be in the right location, that beam of emission will sweep by our position every time that neutron star makes a complete rotation.
Yep.
And so we see these rapid flashes of, initially discovered at radio wavelengths. Today we know that emission can be at all different wavelengths, radio all the way up to gamma rays.
I was also going to say, we definitely have picked it up in the optical wavelengths as well.
Yeah, we even picked it up in gamma rays with the Fermi.
Gamma.
Yeah, the Fermi Gamma Ray Space Telescope has detected pulsars at those very, very short wavelengths. And so this whole idea of the fact that they could be a neutron star will explain the pulsar event. One of the things we look for is there a pulsar at the center of the supernova remnant from 1987A? And we haven't detected any yet. Now, you could say, well, it's just that it happens to be pointed in such a way that it never hits the Earth.
Except that magnetic field is going to energize the gas around it and send out radiation from that.
Well, the supernova remnant is close enough. With high resolution, one can look near the center to try to see if there's any signs of something there.
Right.
But the problem you have is what you see as the keyhole material. There's material in the way, even near the center.
Okay.
It hasn't been enough time to clear enough of that material around the center of the explosion to allow us to see down in the very center of what's going on. Okay.
Oh, okay.
Now the other possibility is that the object just collapsed into a black hole, right? And that would be, unless there's material near the black hole giving off radiation, we can detect it like at X-ray wavelengths, you're not going to see it. So an isolated black hole would be invisible in terms of it wouldn't emit light of any wavelength.
Right.
But the other thing that could have happened is that a neutron star formed to begin with, and then mass kind of fell back on top of its surface, pushed it over that magical limit where it collapsed into a black hole. That magical limit is somewhere around 3 times the mass of our sun, and then it collapsed ultimately into a black hole. So there's several of these possibilities. What a perfect object, though, to test these possibilities, to test the different ideas that people have, because it's so close to us. So we can look at it with very high resolution. In fact, in the future, as we get to even higher and higher resolution, you can be sure people are going to be looking at this thing like things like the next generations of the Event Horizon Telescope that was able to resolve the black hole at the center of our Milky Way and the center of M87.
Oh, yeah.
They could look at the center of this when the conditions are right.
And it's radio wavelengths, so it should pierce the material.
Well, and the other thing is that these black holes, since they came from a star that was about 20 solar masses when it was on the main sequence, happily converting hydrogen to helium, that's going to produce stellar mass black holes, which are really small in size.
Right.
The ones that are in the center of galaxies are many, can I add another many times larger. So it makes it a little, even though they're further, well, the one that's in the center of our galaxy is actually close, is only closer to us than this. That's only 26,000 light years away.
Right.
And we barely resolved that. So, and that's on the order of 4 million times the mass of our sun. How would you observe something that was on the order of, well, just a number somewhere around 5 solar masses, let's say, for sake of argument? That's 168,000 light years away. We don't have the technology to resolve that.
But it could pierce that material with a radio telescope like that, and because radio wavelengths get through the dust better and pick up disturbances in it that could say that there's a pulsar with its magnetic field turning.
For the pulsar, but even for
for a black hole.
Well, for the black hole, you imagine we have to wait 50 years for technology to advance. Well, that's 50 more years of that supernova remnant expanding outwards. And then making it thinner and thinner, the material that's in the way of us to look down into the center. That helps,
Absolutely.
So over time, things will just get better. But right now, we do not know what's at the heart of the supernova remnant. It's a very interesting question, from that perspective.
That's probably why they turned James Webb at it, because you've got an 8-meter telescope, essentially.
Well, 6.5 meters.
6.5. Right. That sees an infrared, which gets through dust rather well.
Yes.
And so I can see why this was a target for James Webb almost immediately on its operation. So
now, I did mention the fact that we think it's approximately 20 solar masses. We don't know its exact mass, and that sort of begs the question, how do you determine the masses of things in the sky? So, for example, if the sun was, or let's say a star that is identical to our sun, right? It was somewhere in space. It was all isolated by itself. How would you know the mass of it? If someone told you it wasn't identical to our sun, because then you'd say it's just 1 times the mass of the sun, of course, right?
Right.
But if you didn't know the mass of that object, that star, how would you determine that?
I would look at other stars that were like it, that were in binary or multiple star systems, because Kepler's laws and Newton's law of universal gravitation can determine the masses of the objects that are in orbit around each other.
Exactly. It'd be like asking, how did we determine, or how would you go about determine very accurately the mass of Pluto?
How fast it's going around the sun, its distance from the sun.
What you would do is you would send a spacecraft that would orbit Pluto.
Oh, okay, yeah.
And you'd watch the orbit that spacecraft makes.
Right.
And there, as you alluded to already, there is a direct relationship between how long it takes a spacecraft to orbit a body like Pluto,
right,
and how far it is on average from the center of that object. And that's Kepler's third law.
Kepler's third law.
And mathematically, it would go like the period squared is proportional to the semi-major axis cubed. The semi-major axis being the average distance of the object to the center of whatever you're orbiting.
Right.
So since the spacecraft mass, you either know it precisely because you know what it was when it left the Earth, and you know how much fuel you consumed, but it turned out if you're trying to measure the mass of an object like Pluto, it doesn't matter the mass of your spacecraft. It's going to be negligible
compared to the mass
of Pluto. So you could watch its orbital motion, and that'll directly give you the mass of Pluto very precisely.
Fair point.
And the difference there, whether you can ignore the mass of the spacecraft, it would be like if you asked me, Wayne, what is the mass of the Earth? And I would be a smart person and look at you, Robert, and say, do you want it with people or without? Well, it doesn't matter. Because
Even
the mass,
8 billion of us, who cares?
the mass of people is negligible compared to the mass of the Earth. Even if they somehow all coordinated and jumped away from the surface of the Earth at the same time, and for that split second, they were not part of the Earth.
And the Earth would go, something happened?
So the mass of the Earth is so many times greater than the mass of all the people combined, you just don't worry about it. That's why we never say that. What is the mass of the Earth? Well, is that with or without people? It's irrelevant, totally irrelevant.
Right.
It's the mass of the Earth. It would be the same value.
I would also argue it's an irrelevant question because we were part of the Earth. You know, I mean...
Well, you want to know what is the mass of the Earth. That's a very much a relevant question.
Yes,
You're thinking about
I agree.
comparing planets
we're part of that,
and all
so
that,
why would
right?
you discount us?
Yes, right, exactly. So anyways, there's this kind of thing. That's how we measure. So Kepler, but how do you measure the mass then of a blue supergiant 168,000 light years away? There's nothing going. It's not in a binary system as we know. Now it may or may not.
Look at other blue supergiants.
Exactly. So these are always these estimates, you see. And in science, when you use information like that, you can estimate that its mass is like 20 plus or minus a couple solar masses, right? That's kind of the thing that you look at.
And that is how these masses are labeled in a catalog is they're 20 solar masses plus or minus 12.
Yeah, so you can tell exactly what type of star it is, at least based on the spectra that you have, which is measurements of how it's the change in brightness of the star as it relates to wavelength, and compare it to things that you've estimated better, their masses, whether in binary systems, two stars going around each other or so on, to eventually, hopefully, that you constrain the total mass of the object. In this case, you're constraining the mass of the progenitor, the one that blew up. And you know it has to be greater than 8 times the mass of our sun. Or
because it blew up.
Because it blew up as a type 2 supernova, right? It wouldn't have done that if it wasn't a massive star.
Yep.
So right away, that puts you in this ballpark of what remains is a neutron star or black hole. And since we don't know precisely what was there to begin with, we have a hard, time. It's a hard because it's near that border limit, a boundary layer between being a neutron star and being a black hole, and we don't know. If it would have been like a really massive star, 50 times the mass of our sun, then it was, definitely a black hole.
It physically, by the laws of physics that we know, it couldn't blow off enough mass at that mass.
Right.
To not avoid being a black hole.
Yeah,
so.
But this progenitor was on that border area, so that's why there's such an uncertainty on what remains afterwards.
Cool.
Okay, so we're going to move on to the next one.
All right.
Now,
so another neat little thing.
So we're talking about the James Webb Space Telescope, and one of the tasks that James Webb Space Telescope is being used for is the detection of planets going around other stars, and try to not only detect them, but maybe try to find out some detailed information about their atmosphere, like composition.
Right.
So what are the things that you would like to look at an atmosphere of some planet? Let's say it's 40 light years away, and you're able to taste its atmosphere. That is, determine its composition.
What do you see its spectrum?
Yeah, what would you look for to maybe determine whether there's some type of life on that planet?
I definitely want to look for water. I definitely want to look for free oxygen, and probably methane and some hydrocarbons. Hydrocarbons would be there because that would be an indicator of a technological civilization.
Yeah, a technosignature, correct?
Right.
Well, to do that, one of the obvious things one should do is say, what can we see in the Earth's atmosphere?
Absolutely.
And so this actually was done recently. So this paper that you can see the title in the abstract was actually just submitted online at the end of August, essentially, this year. And what they did basically, the team of researchers, is they looked at light passing through the Earth's atmosphere, and that light was captured by a Canadian spacecraft, is actually known as the SciSat satellite, and that looked at what we call the Earth's transmission spectrum. So as the light passes through the atmosphere of the Earth and then gets detected, the atmosphere imprints on it different features. And these features are related to the composition of the atmosphere. So if you go to the next slide, there's a good example of that. So this is what we call the Earth transmission spectrum. And you see the different emission lines, if you like, that are shown there. They're actually how the light then passes through as it relates to altitude. So they're not emission lines in the sense of a spectrum that we normally used to, but just the effect of what the different heights in our atmosphere has on the detection of these molecules. So whether you detected it as absorption lines or whether you detected them as emission lines. You can imagine at night you have the sky glow. And so the light is being emitted from these molecules. In the daytime, as the sunlight passes through the atmosphere observable by a satellite, then certain molecules and atoms will absorb that light. In that case, that's an absorption line spectra. So we're looking at how the light is transmitted through the Earth's atmosphere as it relates to both wavelength, which is plotted along the horizontal direction, so-called x-axis if you like, and along the vertical direction is the height above the ground, in terms of the effect that the different molecules have on the light that passes through the atmosphere. And what you see here is some prominent molecules that we have in Earth's atmosphere, such as CO2, carbon dioxide. And you can see large peaks related to not only CO2, there's one there sort of into the right of the middle due to oxygen, O3. But if you look very carefully at some lower level ones, you see evidence of water, H2O, and look now on the right side, sort of to the right of that O3 height that you see there. Notice what you see labeled, CFCs. Now, Robert, could you tell us all what a CFC is?
Chlorofluorocarbons.
And what type of molecules are those?
Well, those are large chain hydrocarbons that have a chlorine atom attached to them. They are devastating to the ozone layer, and we've been slowly getting rid of them. They are exactly what I was talking about and what Wayne called a techno-signature. If you see CFCs in an atmosphere, you have a technological society going on.
Now, wouldn't you love to be able to see that in the atmosphere of a planet orbiting a star 40 light years away?
Oh, I'd be dancing in the hallways, screaming and hooting and hollering.
Because that would prove that there's life on that planet, at least
Absolutely.
some form of life that contaminated the atmosphere.
You do not get CFCs by natural processes.
Exactly. So the only thing that would cause it would be life. And in fact, because it's CFCs, rather an advanced life. We're not talking about bacteria.
We're talking industrial.
We're not even
stuff.
We're not even talking about dinosaurs, unless they got their coal-fired planets going, right? We're talking about man-made chemicals that are released into the atmosphere, or human-made chemicals.
Industrial chemicals.
Exactly. Exactly.
So,
now,
cool.
So this is what the Earth looks like, and we know the composition of the Earth's atmosphere. We can directly sample it. It's no big deal. But then you ask, what would the Earth look like from a distance of 40 light years or 50 light years? Would we be able to detect these type of signatures? So if you go to the next slide, this is what we're seeing. Now, the top slide is what we would see using data from the NIR-SPEC instrument on the James Webb Space Telescope, and the panel or figure on the bottom is what we'd see for the other spectrometer that's on the James Webb Space Telescope, MIRI. And so notice that the spectrum of the Earth has been altered so that it's much poorer resolution with more noise added to it, and it would give us equivalently what we think the Earth would look like if we had the same type of transmission spectrum that we've seen in the previous slide, now taken from an object that's at essentially the distance of the TRAPPIST-1 system. Do you remember that system?
I remember that one. That was one of the 7 planets. And at least 4 of them are in the quote-unquote habitable zone.
Right, and no sign of Snow White.
And no sign of Snow White.
With the 7 planets, right?
Well, it's the dwarf star and not the dwarf planets.
But if you have an Earth analog, I should say, of the Earth, that is a planet like the Earth in terms of its atmosphere, and it was at the location of this TRAPPIST-1 system, would we be able to detect the possibility that it had life on that planet? Well, this is what you want to look at.
This is what you want to look at. And everything I'm seeing says there's a possibility of life, but there's nothing definitive in either of these spectra.
Right, so we see the presence of oxygen.
Right.
You see the presence of carbon dioxide.
You see O3 and CH4, methane.
You see presence of water, potentially.
Mm-hmm.
And in the CFCs, which were like the guaranteed 100%, they're just down in the noise.
They're down in the noise.
Unfortunately.
Drat.
So that would give you some idea how far you can go in terms of the limitation of the James Webb Space Telescope to detect our atmosphere that would have signs of technosignature, right? It would be a technological society that existed or
So we
does
don't
exist
have
on
the
that
technology yet to pick up something like that.
Not to give a definitive type of thing that you
Right.
could say 100% sure there's life on that planet, right? There's a lot of hints here.
There are hints. I mean,
Oxygen being a
O3
big one.
means that you have free oxygen, which free oxygen hits strongly at life because oxygen is nasty, nasty, nasty stuff. It reacts and combines with everything. And so oxygen, if it's not being replenished from somewhere, is going to rapidly get out of the atmosphere. The same thing with CH4, with methane.
Now, in the early Earth, was there any oxygen in our atmosphere?
Very little.
Very little. So where did all the oxygen come from to make up, what, 20% of the Earth's atmosphere today?
And that was from cyanobacterial action.
In other words,
Photosynthesis.
life.
Yep.
It comes from life.
Right.
So if you see a lot of oxygen in an atmosphere, it doesn't say for sure 100%.
It doesn't say for sure. There are natural processes that will put oxygen into the atmosphere, or non-life, I should say, natural processes that will put oxygen into the atmosphere. It's just it won't last for very long. You know, and when I say very long, I mean thousands, tens of thousands of years, and it's gone again.
So if you detect such a planet, then things become very interesting. In fact, that would be a great motivation to have essentially a very large telescope, much larger one than the James Webb Space Telescope, to be able to make observations of those type of targets to see if you can see anything like technosignature, like CFCs and so on.
Yeah. And Mizuho has asked a very good question. Why are the error bars so large? And does it have to do with wavelength? And the answer to that is yes. If you notice, the error bars get larger the longer the wavelength down at the bottom, so that when you start getting up at about 10 micron or so wavelength, the error bars become so large it's hard to see anything through the noise.
Right, and in this case, it's due to the sensitivity of the instrument. So remember, this is the Earth spectrum, transmission spectrum, that now it's been displaced to 40 light years, but then you have to observe it with the James Webb Space Telescope. So that introduced all of this noise, if you like, these large uncertainties in the data we expect to receive from an analog of the Earth. So the sensitivity of an instrument changes with wavelength. And you can see that clearly here, that the near-infrared detector is a lot more sensitive than when you get to really far wavelengths like 12, 13 microns and longer.
Right. Yeah. I got to admit, I wouldn't trust this spectrum out past about 10 microns.
No, exactly. That's the way you should be thinking about this data set
itself. Where do you stop trusting it?
Right. But it's interesting to know, I mean, that gives you in science, right, where you say, for example, you don't believe a detection unless it's at least 5 sigma. That's the detection signal related to its noise. So we always look at what we call the signal to noise ratio. Mm-hmm. And that's where that comes into play here.
Absolutely. I mean, it's still a thing of beauty. I mean, that you can pick up CH4 and H2O and CO2 at those kind of, even O3 at those distances with James Webb just is phenomenal. Holy cow.
Well, here's another thing to think of. CFCs, if you're really intelligent in terms of the society, would you have a lot of CFCs in your atmosphere?
Probably not. But at the same time, I would also not sure I wouldn't look at microwaves for CFCs simply because they have a lot more rotational and vibrational energy levels than they do necessarily electron transition energy levels.
Well, imagine a civilization that's been around for hundreds of millions of years,
I would hope they would
advanced.
clean that out of
That's
their
what I'm
atmosphere.
thinking about. This signature of CFCs, that may be just transitory. It might be just there for a few thousands of years and then it goes away.
Because we're cleaning them out of our atmosphere.
Exactly. I mean, I remember back in the 70s, there was a big push to get rid of spray cans, like aerosol cans that contain a lot of CFCs, because that was going up, destroying the ozone layer, allowing more ultraviolet to get to the ground, causing problems.
Causing skin cancer.
Yeah, higher incident rate of skin cancer. I mean, you think of Jimmy Buffett, right?
Right.
Who just passed recently from skin cancer. So you could attribute that to his lifestyle,
Yep.
or the fact that, our ozone layer did take a hit, especially in the early 70s, right? And so that we're trying to repair that, today by having all these regulations that we don't release, the amount that we had in the past.
Yep.
Okay, Robert, so you had some things you would like to talk about.
Well, kind of in the spirit of what you showed with your first slide, I got to remembering some comments that I've seen on about that first slide, that Russian probe be hitting. And I've seen comments from people going, yeah, we can see that, but we can't see the Apollo landing sites. Well, guess what, folks? We saw those back in 2009 with a satellite mission that we've mentioned earlier in the show today, LRO, Lunar Reconnaissance Orbiter. Now, LRO took this picture of the Apollo 17 landing site back in 2009. And you can see clearly the descent the descent stage that dropped to the surface of the moon. You can see the tracks the astronauts left. You can see the little buggy where it was finally parked over on the right side of the screen. The lander is there in the center. You can see the paths they took to set out equipment, the LSEP equipment, which did various monitoring.
So you know what LSEP stands for? Do you remember?
No.
Apollo Lunar Science Experiment
That's
Package.
It. That's it. Yeah.
That's like seismometers and stuff to measure moonquakes.
Right. Now, keep in mind, LRO is also orbiting the moon at a distance of 50 kilometers, about 31 miles. So people go, well, why don't we have a better picture of it if it's that close? Well, a plane flies at about 30,000 feet, so about 5.7 miles. Okay? How well does your camera pick up cars on the interstate from that altitude? Now imagine LRO is 6 times that height. This is a really good image for that kind of height difference. So LRO did a great job. This is Apollo 17's landing site. This is Apollo 14's. And it even got a pretty good, as you can see from the inset, view. You can tell that that's the lunar lander module. So these images have been taken of the lunar landing sites. And, honestly, there's no denying what they are. You can see the footprints.
Well, a couple things to say here. Number one, you can actually see the size or the sense of scale. If you look in the top right, you can see a bar that represents a length of 100 meters, as seen in this image. So that gives you a sense of scale there. The other thing is, you can't tell me, now here we're going to get into conspiracy.
Okay.
You can't tell me that if the United States did not put people on the moon, that by now Russia and China
and
would
Italy
not have raised literally heck in the UN and trying to uncover the big lies that the United States tried to propagate on the rest of the world.
Right. I agree. We're not talking conspiracy of a few hundred employees of NASA. We're talking conspiracies of thousands of people who monitored these transmissions. Sorry, folks. I'm not sorry. We went to the moon. We landed people there. They wandered around. There's their tracks on the surface.
Well, the other thing is we brought back
rocks.
pieces of the moon.
Yeah.
And when you analyze those pieces in a laboratory, and any scientist can get a hold of some of that material, and museums have them, for God's sakes, right?
Yeah.
That the composition of the rocks and soil is not the same as the Earth. It's not identical.
That's one of the critical points about lunar formation that is causing problems, because the oxygen isotopic ratio is wrong for the moon to have come from Earth.
Yeah. So that
It has
just
once been part of Earth.
So if those rocks didn't come from Earth, then how did someone fake the moon landing? Where would they get those rocks from?
Right. oh, well, they're lying about that. Sorry, no, they're not.
Yeah, any scientist can check that. In
It's
fact,
been checked and rechecked and rechecked.
and most of that lunar soil and rocks haven't been touched. That's in storage, right? So that we develop instrumentation in the future, that new techniques will uncover new information about that.
And so that's why it's actually been, most of those rocks have been kept under, sealed and in nitrogen atmospheres, because nitrogen as N2 is fairly unreactive.
And the other thing I noticed is that once in a while you'll see a news article about information that was extracted from the analysis of lunar material, and it was done fairly recently. So when these new techniques get developed, you can apply to NASA to allow you to get small samples of this stuff, right, and be able to analyze it.
I did a presentation on that, and talked about the fact that they had SEMs, scanning electron microscopes, and mass spectrometers in the 60s and 70s when the Apollo missions were going on. But they knew they would get better. They were still a fairly new technology then. Nowadays, we can put spot size in an electron microscope down to 1 micron in size. So, what's a micron? It's a millionth of a meter. So, take something about 3 feet long, chop it up into a million equal pieces, and that's a micron. So much smaller than a human hair, as they say. It's much smaller than most bacteria and even some viruses.
The other thing that I've heard is some people said, this is before James Webb Space Telescope, if we landed on the moon, then why don't we see pictures from the Hubble Space Telescope of the footprints on the moon?
Right. Sorry.
So that would be a question that that people would have if you don't believe that the United States landed or anyone else landed on the moon. And so you can actually calculate, would you be able to see an adult footprint on the surface of the moon if you looked at it with the Hubble Space Telescope in orbit around the Earth? And it turns out you can't. Hubble doesn't have a high enough resolution to see a footprint on the moon.
It doesn't even have a high enough resolution to see the lander, which is about the size of a car, if I remember correctly.
Yeah, I mean, it's several feet is sort of the smallest you can see. It's sort of on that boundary, on that limit, right?
Right.
And so there have been images taken of the moon. You can look them up on Google from the Hubble Space Telescope. It's not like we're forbidden to look at the Hubble.
Right.
It's just that we have much better, higher resolution taken from spacecraft like the Apollo spacecraft when they're in orbit around the moon, right? We don't need to look at it with the Hubble. But now that we got the Lunar Reconnaissance Observer, orbiter, I should say, that's orbiting the moon, and it's a lot closer than Hubble, it can take much higher resolution views. Yeah.
And people don't seem to understand that resolution issue. They see how clear the moon can look through our telescopes here on the ground and say, well, why can't we see these things? And it's like, because the features that you think are so sharp and clear that you're seeing on the moon are kilometers in size, miles in size. They look sharp and clear, but they're still huge.
In terms of scale, what is the smallest object
you can see? From an Earth-based telescope, it's kilometers the object has to be.
Well, even during the Apollo mission, in particular Apollo 11, the first landing, if you listen to what had happened in the past about that, they photographed the landing site as best as they could from spacecraft that were in orbit around the moon, like the previous Apollo 10 mission, for example, and we had orbiters, that were in orbit around the moon, and so on, looking down, taking pictures of the moon's surface, looking for potential landing sites. But even with all that information, when they were actually physically landing and getting a lot closer and seeing better than they ever saw before, all of a sudden they seen boulders everywhere. So that's when Neil Armstrong had to fly the lunar module into a different place because he would have landed on a boulder, and it was set up, the lunar module, that if one of the legs was on a boulder and the rest of them were down on the moon's surface, if that lunar module was tilted too much from vertical, they wouldn't be able to launch properly. Right. So that was scary. You had to land on a relatively flat area, at least right where the lunar module was landing.
And they almost scrubbed the mission, folks.
Well, they're down to their last few seconds of fuel. So that came very close to not making it on the first attempt.
Right. So
resolution is a big thing.
Resolution is the big thing.
Exactly.
And we've talked about that, and that's one of the reasons you want a big telescope.
Exactly. Okay, Robert, I think we're near the end today.
I think so.
And start wrapping up. So just to let people know that we have a very, very special podcast a week from today.
Yeah.
So hopefully some of you can attend in real time, if not watch it afterwards. We're going to have a guest, and that guest is Dr. Omar Lopez Cruz from Mexico. And so he's going to...
So he's coming here?
No, he's not coming here. We're going to actually try the Zoom thing, and hopefully it works better than last week's attempt at using Zoom. So this will be the first guest outside of UND.
Right.
And if this goes really well, and we have all the bugs worked out, then we can start inviting people from afar to hopefully get on our podcast at this time.
That is a goal.
That is our ultimate goal in all of this. So you don't have to just listen to Robert and I banter about every week. We actually have other people that know what they're doing.
That know what they're talking about.
Exactly. Now, we always leave you with a quote.
Right.
But before I say that, we have to plug the fact that if you're interested in science, if you're interested in physics, if you're interested in math, if you like biology, if you have a passion for chemistry, please consider coming here to the University of North Dakota, because we cover all of those topics in our STEM programs.
And a lot of it can be taken online. So I'll always mention that as well as the slides showing. And yeah, please consider joining us. And if you pay us a visit, come by and talk to Wayne or I.
And we love to have people in the arts join us too.
Yes, we do.
We need people that can communicate to the masses. And I don't mean just talk to them or write things down, that do it intelligently, as we looked at several times in the past of the sort of miscommunication that some science, quote unquote, journalists undertake.
Right.
So we got to watch out for that kind of stuff. So yeah, if you like the arts, if you're into that kind of thing, also come and join us. Lots of programs here at UND for you to enjoy. The other thing is, we always leave you with a quote at the very end of all of this, and it's a fitting quote because we talked about planets going around other stars. The quote today is from Giordano Bruno.
Ooh, my man.
He was a very, very famous person who actually was burnt at the stake for his views that life existed in other planets, around other stars, an infinite number of them. But of course, he also harassed the church.
He did.
And that's ultimately, I think, what cost him his life.
Yeah.
Was that harassment. So a quote from Bruno is this: "Truth does not change because it is or is not believed by a majority of people."
Woo.
Thank you very much for listening, and we'll see you next week.
Thank you, folks.